let's talk about integration notation and how to actually find the antiderivative of something. So the antiderivative of something is equal to this squiggly bracket, then the rule that we're trying to antiderive, and then d of x here. The reason why I call this f of x, or the function, and f dash x, or the derivative, is because usually an integration, or finding the antiderivative, is going backwards from differentiation. So differentiation, we go from f of x to find f dash of x. So this is differentiation. Now integration is the backwards of that. We take f dash x and we go to f of x. That's integration. So that's why I write the derivative here, and that gives us our regular function back. But this is just a general notation. You don't have to follow this exactly. But the things that you have to follow are this and this. The first thing is kind of like this squiggly bracket. It's essentially our integration operator. It's just a way of signifying that you're trying to integrate. Then dx on the outside or on the right hand side just tells us that x is the variable that we're trying to integrate with respect to. The same way that if we find the derivative, we write it like dy dx with dx at the bottom. Essentially just a way of saying that x is the variable that we're trying to differentiate with respect to. But this time it's talking about integration. Okay, so now let's jump into our rules. The first of these rules, and arguably the most popular one, is the power rule, when we have something in the form of x to the power of something. So the integral of x to the power of something is x to the power of that something plus 1 divided by n plus 1 and then plus c on the outside. So we might notice that this is the backwards of our derivative power rule, and that's exactly what it is. So for derivatives, we might know that you multiply by your power and then you minus 1 from that power. So in this case, it's just the backwards of that. So you add 1 to your power instead of minusing, and then you divide by that new power instead of multiplying. So in this case, it's x to the power of n plus 1, and then that's all divided by n plus 1, which is that new power. That's all good, but we actually have something extra in this case. We have this plus c over here. Now what that plus c is called, it's called the constant of integration. Essentially, whenever we find the integral or the antiderivative of something, we have this extra term on the outside, which sometimes we don't know what it is. Now, the reason why we have it is we might recall that when finding the derivative of something, we get rid of the constants. So for example, if we have y is equal to 2x plus 1, and we differentiate this, the derivative of 2x is just 2. Now 1 is just gotten rid of. So when we go back to integrate this, there's no way of finding what 1 is, but there might or there might not be a constant there. So just to be safe, we write a plus c on the outside, and then if we're given any extra piece of information, we're able to find c. But because we don't know what that value is, we just write a general plus c on the outside. So let's jump into this next example and let's show how we apply this rule. So we're given dy dx as x squared plus 1, and we're asked to find y. So in this case, y will be equal to the integral, that squiggly line, x squared plus 1 dx. So now what we do is we find the integral using this rule of each of the individual terms. So let's take the first term, x squared. We add 1 to the power, so the new power is going to be 3. We divide by that new power, which is 3, and that's done for x squared. Now, we do exactly the same thing for this 1, but you can see it's not in terms of x, so it's a bit different. What you do is you just make this x. Essentially, it's just that number multiplied by x, so let's say if it was negative 2, like minus 2 from x squared, we just write it as minus 2x. So you just multiply whatever that is by x, and that's a quick way that I like to remember that rule. Then we have plus c on the outside. Again, our constant of integration, because there may be a constant there. So this is the rule for the antiderivative of x squared plus 1. Sweet. Our second rule, which is not much of a rule, but it's just a just a basic simplification of our integration, it's if we have a number on the outside of some rule, then we can actually just take that number on the outside of our integration. So in this case, we have the integral of 3x squared plus 3. So we can rewrite this as 3, and then the integral of x squared plus 1 dx. So this makes things easy to calculate. So you might notice that we have the integral of x squared plus 1 in that calculation. So what I can do is I could just multiply this by 3. And that would give us the rule for the integral of 3x squared plus 3 dx. So that becomes x cubed plus 3x plus c. I don't multiply the c by 3 because obviously that constant is just a constant, so we don't have to multiply it by 3. That just stays arbitrary on the outside. But whenever we have a constant, we can just take that outside to make the calculation a bit easier for us to evaluate. Cool. Now, in general, as mentioned before, an extra piece of information helps find c. So we have the same example here where we have dy dx equal to x squared plus 1, and it asks us to find y again, but then it gives us this extra piece of information. So this helps us find c. So we know from before that the rule for y was equal to x cubed over 3 plus x plus c. Now what this notation tells us is that when x is equal to 0, y is equal to 3. So that we substitute that information in, I'll just write it as a coordinate to make it easier. So 0, 3, we get 3 is equal to 0 cubed over 3 plus 0 plus c. This becomes 0, this becomes 0. We're just left with c is equal to 3. So with this piece of information, we were able to find an exact value for c in this circumstance. So therefore, we know the exact rule for y. Y is equal to x cubed over 3 plus x plus 3, replacing our constant of integration.